Okay, chapter 12, which is some kind of a uh, conclusion to our discussion of oscillations and waves. We are about to be more specific about a very special kind of a mechanical wave. Sound is not an electromagnetic wave. That's why we have a totally different speed for the propagation of sound versus propagation of light and any kind of electromagnetic radiation. So sound, just a few properties, the intensity, the Doppler effect, very well explained with this type of a mechanical wave. It is not just mechanical, you also say longitudinal wave. Remember, it's motion of particles, it's either parallel to the direction or perpendicular. So this time it is parallel to the direction of propagation. And because we live on planet Earth, we have uh, the atmosphere, which acts as a medium to allow this kind of mechanical waves to propagate. So uh, your uh, ears are capable of hearing. Your sound effects can affect your acoustics. And let's say there's a freeway and you want to reduce the noise that is produced by a freeway, you can also do some things for interference and lower the overall noise level from a freeway. So you can do a lot of useful things if you understand the nature of sounds. So we need some kind of a matter. Sound cannot propagate through empty space. Say you want to communicate to the moon, there is no way to do it with just sound because there's very little matter between the Earth and the moon. There's no way for the sound wave to go all the way to the moon. You only can do it with electromagnetic radiation, with light, specifically radio waves. That's a good way to communicate. But sound cannot travel through empty space. But if there is some kind of a matter, say atmospheric, uh, like atmosphere, the air, or say some kind of a solid matter, uh, liquids and fluids. Remember those dolphins? They communicate via sound waves of a certain wavelength and frequency, and the sound waves can propagate through fluids. So, but not through vacuum. And you can see the table that shows you the speed of sound. From all of those parameters, we will be mostly interested in air, of course. So 340 meters per second. This is your main uh, value that you will borrow from this table to solve problems for sound waves propagation. But it's not just air. You can see other types, other elements are also present. What you can hear as a human being starts at about 20 hertz frequency to 20 kilohertz. And unfortunately, the older we get, the less and less range is available for our ears. I definitely recommend you never ever expose your ears to loud noises. Say you like rock concerts so much and it's very loud on any rock concert. If you ever visited, you know how loud it is. This produces a lot of damage to your hearing abilities. That's why your head there's like that ringing in your head right after you were exposed to those loud noises. It's your body telling you, "Yo, it's not good. Stop doing it. You're really doing damage to your hearing range." So Get rid of those earbuds, get rid of those headphones, at least make sure you're using them at a very moderate level of intensity. Those decibels, you can't overload your ears through those headphones. You'll thank me when you'll be at age about 50. If you ignore my warnings, then by age 50, you will not hear anything, and you'll need those special devices, and that's a pain in the behind, and they cost an arm and a leg. It's like smoking, you know? If you start smoking, you're gonna die faster, like much, much faster. If you expose yourself to loud noises, you will lose your hearing much faster. So that's just pretty straightforward. You really, really want to limit your exposure to loud noises. So no headphones, no earbuds, no rock concerts, at least that much. You'll thank me later. Everything that says ultra means beyond. So if 20 kilohertz is the limit, then beyond the limit would be the above 20 kilohertz. And infra means before. So before the limit, so everything less than 20 hertz frequency, that's what we call infrasound, and then ultrasound. And the main parameter would be the intensity, which is the amount of energy that is transported by wave per unit of time across a certain unit area. So remember how there is like work done or energy transfer, and that's force times displacement. Then there is power, which is how fast the energy is transported, or how fast the work is done. So it's work with respect to time. And now it's the power with respect to a certain area, the area that is exposed to a certain wave. Now that would be the intensity. So work is energy transfer, power is how fast the work is done or energy is transferred, and intensity is your power with respect to a certain area. Power is in watts, area is length times width, so meters times meters, you get meters squared. Therefore, intensity would be watts per meter squared. Yeah, and we can detect starting from 10 to the negative 12. This is your like reference point. This is your 0 decibels. Decibels are not System International, but they're kind of useful in case you don't want to deal with those small numbers. And see how it goes as high as 1 watt per meter squared. So instead of the range of 10 to negative 12 to 1, we got a very cool way of describing the intensity as loudness. So what is loudness is a amount of decibels. And the definition is 10 times the log of a ratio between the intensity of the current sound wave with respect to I sub 0, when I sub 0 is your lowest limit of hearing. Remember, human ear detects sound intensity as low as this much, and this is your starting point for measuring the loudness. So I sub 0 is just this lower limit, and everything more intense, like anything louder than this limit, that's what would be the loudness. We'll practice with this formula. You'll see how loudness is calculated. So once again, it's only here to make our life easier when you want to express some kind of a noise, some kind of a sound with a nice number rather than scientific notation with 10 to negative 12. You just refer to this table, and you can see how much easier and straightforward is to describe it with sound level with decibels rather than the actual intensity, which is System International unit. So you start with the 0 threshold of hearing. That's the lowest. And then you can see the radio talk or just me talking right now. It's would be about 65 to 70 decibels. And then street traffic, and then the siren. So see those nice numbers? They really, make sense once you get used to them. It's really it's easier than using this log scale for the intensity. Once again, decibels, that's not System International. Be careful. For System International, for all your calculations of intensity, you have to do the watts and meters squared. Decibels are just for convenience, but they're widely used, and every time you see certain decibels, first of all, you can easily convert to intensity, or if you want to just specify the loudness of a certain noise, you can refer to decibels. Other people will understand you right away. See how rock concert, I just want to point out that rock concert is really the threshold of pain. At some point, the sound is going to be so loud that it's not going to be comfortable for you to stay at that concert. So not only are you going to do some damage to your hearing abilities, you'll just create some painful experience for your body. So no jokes, no loud concerts, no earbuds, headphones, the over-the-ear headphones. This is how you destroy your hearing abilities. Okay, let's take a look at a point source, and there is sound going in all directions. You can think about a sphere that the waves hit, and a certain distance from the source to that imaginary sphere. Let's do the calculation of the intensity. Remember, it's power with respect to surface area. So the more the power of, the louder the noise is, and the further away you are, then you're going to experience a different loudness. If you're very close to the source, if the R is less, then intensity is going to be a big number, like a large number. If you're far away, though, R goes up, the distance goes up, intensity goes down. And I want to point out that this is your perfect example of inverse square law. Remember, we had one for gravity, the universal law of gravity, when distance squared defined the force of gravity. We have one for electricity, which is Coulomb's law. We have one for magnetism, which is Biot-Savart law. Now we have one for waves and optics. This is your inverse square law that connects the intensity, or if it's light, you would say brightness, to power, which for light would be luminosity. So for any, say, light bulb, the luminosity would be like, say, 60 watts, which is printed on the light bulb. But if you're close to a light bulb, it's going to be brighter. If you're further away from a light bulb, it's going to be dimmer. So for electromagnetic radiation or mechanical waves, you still have the same inverse square connection, which also, proves the inverse square law to be one of the fundamentals of the universe. This is not a biology class. You don't have to describe the ear and how it responds to the change in atmospheric pressure, which is what the sound waves are all about. But just understand that it's a pretty complicated setup, and you have to take care of your ears, because your ability to detect certain frequencies is a gift. It's a privilege. So don't waste it. Don't lose it. Once again, do not expose yourself to extremely loud noises for long periods of time. Say rock concert, you really want to stay away from the stage as far as possible, because otherwise you're going to do damage to your hearing abilities. So this one is out of the test. We're not talking any formulas here. Biology class will definitely torture you with the knowledge of all the pieces that make up the canals, the anvil, the hammer, and all the stuff. Not me. Also, I'm doing you a favor and cutting the musical instruments out of tests. There is a formula that connects the how fast the wave propagates with respect to the tension in that string. That's why you hear different noises coming from any kind of a string instrument, say a violin or I don't know, a piano. It's all the tension in that string with respect to what the material is. See, the mu is the mass per unit. The point is, you don't have to worry about it for the tests, but if you're into music and you want to know the physics behind, go ahead, practice with this formula, and everything's good. See how piano is still the same idea. It's the string that is under tension, and you hit that string, and that's how the oscillation is created, and a sound wave propagates through the air and hits your ears, and you can enjoy music. Yeah, if it's not a string instrument, then you have just wind instruments that you have to blow air into, and then use the openings, because those wave patterns will follow a certain wavelength. So playing with those openings will create a different frequencies that you can get out of the wind instrument. Once again, none of that is on the test. And also interference with diffraction, that's just a separate lecture just for interference and separate lecture for diffraction. There's a lot of information here. It's all pretty much simple and straightforward, but it's just a lot of practice with different setups, and you have to do a lot of geometry here, which you can see how two waves interact with each other. Sometimes they one wave is in the maximum, the other one is a minimum, they get together and you hear nothing. Sometimes the waves are both in the maximum, and you will hear the increase in amplitude. You'll hear a louder noise. So that's the main idea. And once again, it's out of the test, so you don't have to worry about it. However, I still encourage you to read the text and see the sample problems, at least, for what is there. Once you hit the physics of optics, you will be exposed to interference and diffraction anyways, so let's just postpone that experience till you get to optics. Yeah, so constructive interference, destructive interference, any of that is a definitely good topic for discussion, but we are really short on time and overall practice for those things, so none of that is on the test. But Doppler effect is, the reason for me to include the Doppler effect is because no matter what kind of engineering career you choose, you will probably use Doppler effect in your life, because first of all, it's not just for sound. Any wave will show the Doppler effect. And if you want an example right away, I want you to focus on what kind of sound waves you hear when, say, a police car comes towards you, and then compare that to what you hear when the police car is moving away from you. And if you haven't noticed, I can tell you that when it's towards you, it's going to be like wow, 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 like higher pitch, higher frequency. And when it's going away from you, you will hear like wow, 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 which is a lower pitch. So what's going on here? That's what we call the Doppler effect. So Doppler effect can easily tell you if the object is coming towards you or away from you. And for light, we have a term that says blue shift. That means the wavelengths are shifted towards the color blue on the electromagnetic spectrum versus redshift when the wavelengths are towards the red color on the electromagnetic spectrum. So blue shift means it's towards you, red shift means it's away from you. And that's how you can tell that a distant star that emits a certain light is going towards you or away from you. You'll say an asteroid or anything else. Like from astronomical perspective, Doppler effect is definitely a big deal to tell you what's going on far, far away. And you don't even have to go there. You just measure the light coming from those objects, and it tells a lot. So here on Earth, we also use Doppler effect to do the geology. You know how geologists, they're looking for new resources of different minerals and oil and gas. So how do they know where to drill? Well, they use sound waves to go all the way into the ground, and then they catch the reflected signal. And the difference between what they emitted and what they caught is what we call Doppler effect. And using the Doppler effect, they can tell if there is some oil or gas beneath the surface of the Earth. So very useful for geology to, find new sources of minerals. So once again, Doppler effect is a uniform thing for any kind of wave, and understanding the physics behind it will definitely benefit you in many different areas. So if the truck is sitting still, if there's no motion of the source, then the person behind and the person in front will hear the same frequencies. So no Doppler effect. If there's no motion, no Doppler effect, no change in frequency. And if the truck is moving, say, to the right, then what you see here is the person catching higher frequencies, shorter wavelengths, and the person behind hears lower frequencies and wider wavelengths. So that's the Doppler effect. And the change between the frequencies can tell you how fast the truck is moving. And one more application, of course, is the police radar. That's how they one, two. So the headset turned off. So that's how the police knows how fast you're going. If you are going to be given a ticket or you're within the limit, so you're not going to get a ticket. So another application is a police radar, police gun that measures your speed. So yeah, the difference between the waves is your D, and that's what we call the wavelength. Distance is speed times time. Nothing new here. And there is a rigorous derivation for the many different cases when the source is coming towards you, when it's away from you. And the textbook has 4 different formulas as a result. I really don't like memorizing all 4 cases. I mean, you can do it. You can read the book and go with all those results. So you have 1, 2, 3, 4 different cases with different formulas. And I suggest that instead of memorizing 4 different cases from the book, you follow this little formula, which is just one formula, and it takes care of all the possible scenarios, because you see you have plus minus on top and minus plus at the bottom. It's very important to keep it this way. So what do we have here? This one formula just combines all cases that are derived from the book, and it's like it's a to my mind, it's a much easier way to remember all the possible scenarios for Doppler effect. Here are the instructions. So what you have on the left is the frequency that you hear being the observer. So that's what you register, being either in front of the truck or behind the truck. So you are the observer. That's the frequency that you register. The F by itself, not the F prime, but if F is what the source releases. Say this is the original signal coming from a police gun, right? Police gun emits a signal. The signal hits your body or your car, and it's reflected back, and the police gun detects the reflected signal, and the change between the signals, that's what tells the policeman how fast you go. So this is what you register as an observer, and this is what was emitted by the source. V is the speed of the wave. And depending on what kind of wave, you have options. For sound, V is going to be the speed of sound. And the speed of sound, we discussed that here. Speed of sound in the air is about 340 meters per second. So for all of your problems, your V here is going to be 340. If you want to use Doppler effect for light or any other kind of electromagnetic radiation, which is a form of light, then this is going to be the speed of light, which would be a million times more. It would be 300 million meters per second. So for sound, this V is 340, no matter what. Now VD is the speed of the detector. You might say, hey, I'm just sitting still, I'm standing still. Well, then your detector is just zero. Or let's say the police car is not moving anywhere, then the speed of the source that you have at the denominator can also be zero. So that really depends on the problem. Is it the detector that is moving back and forth? Is it the police car that is moving towards you or away from you? Well, all of the possible cases are covered here. So this is the frequency that you normally would be looking for. This is the original signal. V is the speed of sound. And then detector and the source, well, you have to see what's given and how you are going to proceed for what's missing. And the plus, minus, minus, plus is pretty straightforward. The top option is for detector or the source moving towards you. So if detector is towards, then it's a plus. If source is towards you, then it's a minus. And if something's going away from you, it's going to be the bottom point. So if the detector is away from you, is going away from you, then it's a minus. If the source is going away from you, then it is a plus. So once again, plus, minus, minus, plus takes care of cases when it's towards, away, towards, away. Towards is the top option, away is the bottom option. Towards is the top option, away is the bottom option. So for your memorization, you say detector on top, source at the bottom, and then you say towards, away, towards, away. That's how I remember on what to do with this formula. So detector on top, source at the bottom, and it's top, and it's towards, away, towards, away. That's what you have. Anyways, here are the instructions. We're going to solve some problems. You'll practice. You'll see how easy it is to actually do it. Once you get a grip on what's going on, you'll have no problem with figuring that out. A Doppler effect is going to be on the final, so you can't really, you don't want to ignore it because there's going to be a lot of points. And I do have a police radar problem, which is quite challenging because it's like two problems in one. But if you understand what's going on with police radar, then any other problem should be a no-brainer right away. You will figure out Doppler effect right away. So let's take a look at what's going on with the police radar that measures the speed. It emits radiation and then receives some sound waves and analyzes the difference between the emitted signal and the reflected signal. So let's say emitted frequency is 18 kilohertz, and what is detected after the impact to a certain car is at 22.2 kilohertz. So will the target get a ticket? That's a good question, right? We want to know if you're moving fast or not so fast and you're safe, you are within the limit. Let's take a look. Yeah, like I said, it's two problems in one. The first part of a problem is when there is emission by a stationary source. You know how cops, they really hide in the bushes and they're not moving. They try to be stealth. You can't see them up until you're pretty much right in front of them. So they don't want you to see them, and they are sitting still. They're hiding in the bushes. So source is stationary. Okay. So right away you say what? V of the source is just 0 for the first part of a problem. And the speed of target, the moving car is the detector. The moving car is would be the target for that waves that were emitted by a police gun. So the detector is moving at a certain speed that we don't know. We're going to call it U. So U is the unknown speed that we want to measure. And then there is reflection. The signal is reflected by the car all the way to the cop. So for the second part of the problem, what do we have? We have the car, the target becomes the source. It was the detector for the first part of the problem, but now it is the source because it reflects all that signal back towards the cop. So the moving car is going to be the source, and the cop will become the detector. So Doppler effect, you have to apply it 2 times. First time, it's the cop that is the source, and the target is the detector. And then detector reflects it back, and cops are the detectors now, and the target is the source. That's the main idea. So first part, moving target, as I said, source is the cop. So source is 0, so your denominator is just V, and V is the speed of sound. V is 340 meters per second. That's what we can tell right away. Now, what do we have for the top? Is it the plus or the minus? Remember how it's towards away, towards away. So is the detector moving toward or away from the source? Well, the detector is the car, and the car is clearly moving towards the cop, right? The cop wants to measure the speed and probably give a ticket, so it is an option for a plus. You have to go with a plus at the top because the detector is moving towards the source. So it's plus V because the detector travels towards the source. And this is your formula to figure out how, like what kind of a frequency is detected by the target. If this was the original emission by the cop, and the speed of sound is 340, and U is the unknown speed of a car. Yeah, what's given is the emission, so F sub S, it's given. But F sub S prime, it's not what's given. It's what's in between that will be the emission for the second part of a problem. Once again, this is the emission, and this is what's detected. But what is detected by a car becomes the signal for the second part of a problem, where the cop is going to be the detector and receive the reflected frequency from the car. So, yeah, it doesn't mean that this is 22.2. It's 22.2 is what the cop will register as the reflection. Okay. So for the second part of a problem, it's now the COP that is the detector. And it's the source that is the target because the signal is reflected by the car towards the COP. So COP is the detector and source is the car now. So what do we say for the COP? The COP is still sitting still. So your detector is now 0. The COP is sitting still. And the source is still moving. And it's still moving what? Towards the COP. Remember how plus minus minus plus is towards away, towards away. So for towards, you have to go with a negative sign for the denominator. So COP is the detector. COP is sitting still, so it's 0. And the speed of the source is still u. Your v sub s is going to be u. It's the unknown speed that we're trying to solve for. And it's going to be negative because it's towards. So source is going towards the detector. Plus minus, minus plus, towards away, towards away. So minus is for the towards option. So what is registered by the COP is given as 22.2 kilohertz. This is what was reflected by the car that you find from the first part of a problem. V is the speed of sound, 343, and U is the unknown, and it's a negative. We just discussed all the reasons for that to be negative. So you have two equations, two unknowns. It's the first unknown is what is reflected by the car and what is how fast the target moves. So U and F sub S prime are the unknowns. Here is the algebra. The answer is 35.8 meters per second. Convert that into miles per hour if you want, roughly multiply by 2. And it's going to be about 80 miles per hour, which is usually a ticket. You know how cops give tickets for everything more than 10 miles over the limit. If the limit is 65, like on all the freeways, pretty much 80 is a little more than 10 over the limit, and you might get a ticket. So the point is, you have to understand who is the detector and who is the source. And then depending on the kind of motion that you have in the problem, once again, it's plus minus, minus plus, towards away, towards away. That's it. This is what is registered by the observer. And this is what was emitted by the source. We're going to solve a few problems on classroom discussion, so don't worry if you're still not sure which one is which. We'll get some practice. For sonic boom and shock waves, yeah, I'm pretty sure you've heard about Mach numbers for jet fighters traveling faster than 1 Mach, 2 Mach, 3 Mach. Those are just speeds of sound multiplied by a certain coefficient. You have a certain source, and if the source moves faster than the sound propagates, then you will hear that loud boom at a certain point when you cross that speed of sound boundary. Not many equations here. I only have the definition for Mach number for your reference. It's just the ratio between the speed of source to the speed of sound. So if you're traveling faster than sound, then your Mach number would be more than 1. And everything less than that, that would be less than 1. And if you hear 3 Machs, 5 Machs, that just means that you're traveling faster than sound by this many times. That's all that matters here. Yeah, you can see waves everywhere. You see how the duck or the small boat propagate through medium being the fluid here, the liquid, the water, all of those effects that we skipped for interference and diffraction, you can see them in real life. Once again, I will not load you with many things, only the Doppler effect and the loudness idea. But once you hit optics, you will definitely get more practice with calculating the minimum and maximum and the distance between all sorts of parameters, so you can express the waves with mathematical precision. There's one more problem with a plane that flies at a certain speed, and there is a time for the man on the ground hearing the sound, and you can tell what's the altitude of a plane just by solving the triangle with what's given and what's missing. That's the altitude. This is how far the airplane travels through before the sound hits the ground, and reference angle for those two displacement vectors to compare. So how would you solve for how far away it goes? You can connect it to the opposite side of a triangle through a tangent function. Tangent is opposite over adjacent. So if you want to solve for adjacent, you just go it's actually the other way. If you want to solve for the opposite, it's the adjacent times the tangent of angle, and you can solve for how fast the plane goes and how much distance it covers, because x is distance. Distance is speed times time. And if it travels at what? 1.25 times the speed of sound instead of the speed of a plane, you say 1.25 times the 340. That's your speed of sound. And the time is, be careful, not 1 minute. You cannot do minutes. You have to go with seconds. So 60 seconds here. And the reference angle can be found at 53 degrees. And the altitude is therefore, what is it? 34,000 meters, so 34 kilometers. Well, that's kind of high, but that's what jet airplanes like to cruise at, so that they're not detected by radars and other systems that allow us to detect them. But the point is, for all of your calculations here, it's only the distance formula, the speed times time, or the Doppler effect that allows you to measure the frequencies, and that connects to wavelengths and speed of sound or light. So you can tell how fast something goes, and that is the profit from the analysis of a wave's propagation. Other applications like medical imaging, ultrasound, all of that, it's just also the consequence of Doppler effects and sound waves being able to travel through different mediums, and showing the results to our imaging devices. Once again, I'm not going to load you with any ultrasound or medical imaging. Feel free to read the book on that. The major focus is the speed of the Doppler effect and the loudness. Loudness is your part. This formula. This is the main application at the introductory level. Okay, gonna pause the recording.